Out in the vast, uncharted reaches of space, a comet named 3 Atlas defies every known rule of existence, lingering where no such object should be. On October 14, 2025, a test satellite released groundbreaking data backed by over 9,000 crystal-clear images that not only confirms this anomaly, but also points to a shocking possibility, a deliberate cover-up by forces unknown. Tonight, we peel back the layers of this cosmic conspiracy, presenting irrefutable evidence to solve this mystery once and for all. But the wonders don't stop there. We'll also venture into the enigma of a distant star that pulses with eerie precision every 44 minutes, emitting radio waves and X-rays in a rhythm that has astronomers stumped. Is this a new addition to the catalog of mysterious cosmic phenomena? Meanwhile, closer to home, 4 colossal coronal mass ejections are barreling toward Earth, their dazzling effects potentially lighting up our skies and disrupting our world this very week. And if that's not enough to spark your curiosity, we'll dive into the astonishing tale of the ghost particle. A neutrino so extraordinarily powerful, it shattered every known record, crashing into our planet with an energy once thought utterly impossible. Stay with me until the final moment, because what we'll uncover together will fundamentally transform how you perceive the unseen forces watching us from the cosmic abyss. Leave a comment below with your location, the local time, and your honest take. Are we being fed the full truth about these earth-shattering discoveries? Want to fuel this community's growth? Share this video on X, Facebook, Reddit, or your group chats. Every share, comment, and click powers our pursuit. You're the heartbeat behind our relentless chase for these stories. Want to help our community grow stronger? Share this video across X, Facebook, Reddit, or even in your group chats with friends and family. Your support is the heartbeat of our mission to chase these extraordinary stories, and I'm deeply grateful for every one of you standing with us on this journey. The Part 1. The Enigma of 3 Atlas. Tess speaks, no tail. Those 2 words shatter the familiar tale of a comet. Picture a night sky bristling with telescopes, each a multi-million-dollar marvel, all trained on a singular target. Hundreds of instruments, from sprawling ground-based observatories to spacecraft drifting in the vast silence of space track. One fleeting object streaking through our solar system. Now imagine the most sensitive of them all, after stacking over 9,000 images, delivers a revelation no one saw coming. There's no tail. On October 14, 2025, astronomers unveiled a colossal data analysis from TESS, the Transiting Exoplanet Survey satellite. They scrutinized more than 9,000 frames of 3 Atlas, an interstellar visitor stirring chaos since its discovery. Using a technique called co-adding, they stacked these frames to amplify faint signals buried in the cosmic noise. It's like layering whispers of light, frame by frame, until the faintest glow becomes clear, a process akin to turning up a barely audible song until the lyrics ring out. What Tess revealed, or rather didn't reveal, was staggering. 3 Atlas appeared as a mere pointed dot. No sprawling coma, no wispy cloud of dust and gas, no iconic tail streaming from the sun. The radial brightness profile, how light fades from the object's center, plummeted like that of a star, not a comet. Stars so distant collapse into a single pixel, their vastness reduced to a pinpoint. Comets, by contrast, should unfurl, displaying structure, their tails weaving tales of awe and dread across millennia. Every telescope has a point spread function, a unique fingerprint of light from a point source. When Tess examined 3 Atlas, it saw only that fingerprint, nothing more. The analysis was precise. If dust existed beyond a certain brightness, it would have shone through. The stacking boosted the signal-to-noise ratio so sharply that even the faintest features should have emerged. Constraints on dust density, particle size, and ejection velocity all pointed to one conclusion: whatever dust might be there, it defies the behavior of comet dust. Yet other observations tell a conflicting story, and this is where the mystery deepens. The James Webb Space Telescope detected water vapor and carbon dioxide around 3 Atlas. Spectroscopic data revealed mass loss volatiles escaping into space, hallmarks of a comet in action. But where's the tail? Where's the visible trail of material streaming away? The paradox is inescapable. Either the coma is so dense, so tightly bound, that it remains invisible to optical telescopes, while still emitting detectable gases, or something entirely different is at play. It's like watching a campfire burn without a wisp of smoke. Either some unknown force compresses the smoke into invisibility, or what we're calling a fire isn't a fire at all. The contradiction looms large. TESS, with its unmatched sensitivity for faint extended structures, stared at this object for months and saw nothing. Yet other instruments, tuned to different wavelengths and physical processes, insist something is happening. One of these observations is missing a critical piece, or our entire understanding of comets is teetering on the edge. What haunts me is this: comets have surprised us before, but never like this. Never has an object so perfectly mimicked a point source while flaunting chemical signatures of vibrant activity. The numbers don't just misalign, they clash head-on. This isn't a quirk of observing conditions or instrument quirks. It's a fundamental rift in what we believe this object is doing. The test data is public now. Anyone can download it, run their own analysis, verify the numbers. The no-tail finding stands firm, so we must unravel what's happening. If conventional comet physics can't explain this, we may need to entertain ideas that feel unsettlingly strange. But first, we must probe the depths of this contradiction and uncover why different instruments paint such wildly divergent portraits of the same enigmatic visitor. Part 2. The puzzle deepens. The James Webb Space Telescope, JWST, a $10 billion marvel of infrared astronomy, turns its golden mirrors toward 3 Atlas. Its observations are unmistakable carbon dioxide water vapor, a gas-rich coma teeming with volatiles. Spectrographs catch molecular signatures, emission lines revealing excited atoms, vibrating molecules, and gases streaming from the nucleus. Yet ground-based optical telescopes report starkly different tales. Some see asymmetries, others barely detect anything. Different instruments, clashing stories. What's going on? The answer lies in what each instrument measures. JWST, operating in the infrared, captures wavelengths where molecules glow as they vibrate and rotate. It's exquisitely sensitive to gas, detecting the chemical makeup of the coma without relying on reflected sunlight. It's as if JWST hears molecules singing in the infrared, their songs vivid and unmistakable. SphereX, another infrared mission, echoes this, reporting high carbon dioxide to water ratios around 3 Atlas, unusual even for peculiar comets. Optical telescopes, however, rely on reflected sunlight. They track how dust particles scatter the sun's light back to us. To reveal structure, dust must spread out, forming visible tails or comas. If the dust is too compact, too close to the nucleus, or if the particles are too large, millimeter to centimeter grains, they scatter light poorly and move sluggishly, resisting ejection due to their mass. Such grains might linger near the nucleus, forming a faint, tight envelope that optical telescopes struggle to detect, even as ice sublimates, releasing gas. Geometry complicates things further. The phase angle, the angle between the sun, 3 Atlas, and the observer shapes what we see. A tail aligned directly toward or away from us could appear foreshortened, effectively invisible despite its existence. Different instruments observing at different times from varying orbital positions face unique geometric challenges. A tail visible to one might be hidden from another, a matter of cosmic bad luck. We've seen such cross-instrument disputes before. Comet Ison in 2013 dazzled in some observations, then disintegrated with telescopes reporting wildly different activity levels. Comet C 2017 K2 showed a coma in some views, yet appeared dormant in others, sparking debates over intermittent activity. But 3 Atlas is different. The divide is stark tail or no tail point source or extended object with little middle ground. Timing mismatches amplify the confusion. JWST observed in specific windows, ground telescopes in others, while TESS watched continuously, but with lower spatial resolution. What if 3 Atlas pulses erratically, ejecting dust and gas in bursts rather than steady streams? One telescope might catch a flare of activity, another only silence. Both report truthfully, yet their snapshots clash. Still, the scale of disagreement is extraordinary. Deep stacking of optical images from professional observatories should uncover faint dust if it exists. TESS, after stacking thousands of frames, sees nothing extended, suggesting either the dust is impossibly compact or absent in expected quantities. If no dust, where does the gas come from? Gas doesn't materialize alone. It stems from ice sublimating off dust grains or the nucleus, both processes that should produce dust. The contradiction forces a question: can we trust any single instrument? Each sees a piece of the puzzle, faithfully reporting its slice of reality, yet the pieces form no coherent whole. Typically, astronomical mysteries resolve with more data, refined models, or the discovery of subtle effects, like unexpected scattering or unusual composition. But with 3 Atlas, each new observation muddies the waters further. And then there's the spacecraft question, the one that could clarify everything or unravel it entirely. The Psyche mission, traversing nearby space, might have passed close enough to capture a definitive view. If it took images, where are they? The answer could hold the key to 3 Atlas or deepen the enigma beyond imagining. Part 3. The Shadow of Psyche. We've slammed into a brick wall. Earthbound and space-based telescopes, from TESS's unyielding stare to JWST's infrared whispers, all spit out clashing visions of 3 Atlas point source or gas-spewing enigma. The contradictions scream for resolution. Enter the observation that could shatter the impasse, yet lingers unspoken in the public glare: NASA's Psyche spacecraft. Launched to probe the metallic heart of asteroid 16. Psyche, this probe has carved a lone path through interplanetary void, armed with an arsenal of imaging tools. Its primary quest lies ahead, but en route it snaps calibration shots, navigation frames, and serendipitous science glimpses, a ritual as routine as breathing for deep space travelers. You've got cameras. You're hurtling through the cosmos. You capture what crosses your lens. NASA has doled out glimpses, raw shots of Earth and Moon from afar, starfields etched for trajectory checks. But here's where the timeline twists into intrigue. Public ephemeris data, Psyche's arc, and 3 Atlas's hyperbolic dash reveal tantalizing windows. Not a whisper-close encounter, but near enough at roughly 28 million miles, 45 million kilometers, on September 4, 2025, for the spacecraft's gaze to snag vital details. Orbital math drawn from mission blueprints confirms the alignment, a cosmic bullseye ripe for the taking. So where are those frames? NASA's vaults brim with raw mission hauls, from planetary data system troves to Psyche-specific lockers. Most probes eventually unleash their unpolished gems, metadata logs of every snap, every timestamp, fueling amateur comet hunts in forgotten archives, unearthing gems overlooked in the first sweep. Psyche's imager output should lurk there, ripe for the digging. Yet no fanfare heralds raw Psyche shots of 3 Atlas from that razor-edge approach. No press blasts, no data drops. The public record falls eerily mute. This silence could stem from a dozen mundane roots. Let's chase the innocent trails first, for they're as solid as they are unglamorous. Downlinks from deep space are bandwidth famines. Each Earth window chat rations bits like gold dust. Planners triage ruthlessly engineering vitals, first core mission science, next opportunistic extras shoved to the queue. If Psyche snagged Atlas frames, they might idle in onboard memory queued for a later beam down when slots open. Storage is another choke point. Probes juggle finite buffers, ringed loops that purge the old for the new. Unflagged shots get squeezed, lossy compression stripping nuance, or outright erased by fresher feeds. It's the unglamorous truth, not every cosmic snapshot survives the voyage home unscathed. Then lurk the archival gremlins, metadata mishaps, timestamps adrift, headers glitched, or fields mistagged. Veterans of sprawling sky databases know the drill data vanishes not through malice, but misfiling buried under wrong labels like a calibration doodle or stray star cluster, awaiting a sharp eye to exhume it. Bureaucracy offers its own veil. Agencies enforce data embargoes, proprietary peaks for mission crews, timed releases to shield builders from poachers. The Psyche team might cradle those images, now dissecting them in quiet labs, plotting papers before the floodgates creak open. It's the gears of science grinding steady, no shadows, just protocols, patient churn. These threads weave a tidy, conspiracy-free shroud. Yet here's the itch that defies scratching: absence isn't proof of nothing. We peer through fog, blind to the full ledger, what beamed back, what compressed to ghosts, what tagged awry. The metadata oracle remains sealed, its tales half told or locked away. What recourse demand clarity? Freedom of Information Act summons can pry government grips loose. Petition archives unearth logs, mission diaries, instrument tallies, downlink manifests. These ledgers breathe in the ether, summonable by the insistent. The fork looms sharp. If those images surface, they could pierce the veil, marrying Tess's stark dot to JWST's gaseous roar in crystalline truth. If absent, we grapple with the void. Why did a probe with primed lenses miss the decade's stellar spectacle? And if they exist yet evade grasp, a thornier beast stirs whispers of opacity in the grand machinery of cosmic inquiry, probing the soul of open skies. Part 4, Beyond the Comet Veil. We've hit a dead end with archives and instruments, so let's pivot to a bolder question. What if 3 Atlas isn't a comet at all? What if we've been cramming it into the wrong cosmic box from the start? Its defiance of comet norms, point-like in Tess's gaze, gas-rich in JWST's infrared demands, we explore other possibilities. Can any alternative explain the tangled data without snapping under the weight of our observations? Hypothesis 1. Inert body with micro-outgassing. Picture a rogue from another star system, a slab of rock and ice forged in alien conditions. Unlike a comet's vigorous sublimation, it leaks gas through sparse cracks, pockets of volatile ice venting, without the dust storm that paints a tale. This fits JWST's gas detections, while keeping Tess's point-like view intact, minimal dust, no sprawling coma. But the math stumbles. JWST's volatile loss rates are too high for mere micro-cracks to explain without dragging dust along. Sublimating ice doesn't play clean, it hauls particles as it vaporizes. You'd need a bizarrely pure ice layer divorced from dust, a geological oddity that strains belief. Hypothesis 2, Fragment cloud. What if 3 Atlas isn't one object, but a tight swarm of fragments, too small to resolve individually, moving as a unit like a flock of starlit birds? Each shard leaks gas and dust, but the material stays confined within the cluster, never forming a classic tale. This could explain the point-like appearance Tess sees the swarm as one dot if the fragments huddle closer than our telescopes can discern. Gas spread across many tiny surfaces might scatter differently, dodging optical detection. Yet why do these fragments cling together? They'd need a collective gravitational tug unlikely for small bodies over interstellar gulfs. And even a tight swarm should betray some fuzziness or elongation. Yet Tess sees none. Hypothesis 3. Electromagnetic cage. Now we venture into the exotic. Imagine dust around 3 Atlas charged and trapped by a magnetic or electric field strong enough to defy gravity's pull. Charged grains can levitate, dancing in tight orbits, as seen in planetary rings or plasma labs. If 3 Atlas carries a charge, its dust might hover close, invisible to optical scopes, seeking extended tails, while gas harder to confine electromagnetically escapes for JWST to catch. This neatly ties the compact appearance to the gas signatures. The hitch. No known mechanism lets a passive body generate such fields. You'd need an active process, a power source we can't yet fathom. Hypothesis 4. The artificial gambit. Here's the leap that makes scientists flinch. What if 3 Atlas is engineered? An artificial construct could explain it all. Active systems venting gas without icy sublimation. Reflectors causing brightness shifts a compact form, mimicking a point source. Electromagnetic signatures, if found, would be expected, not baffling. But extraordinary claims demand extraordinary proof, and we have only anomalies, contradictions, not confirmation. This hypothesis teeters on the edge of speculation, awaiting evidence we don't yet hold. Each model makes testable predictions. Micro-outgassing suggests faint dust might emerge with deeper stacking. A fragment cloud implies subtle structural shifts over time. Electromagnetic effects call for polarization quirks or radio signals. An artificial object might reveal geometric patterns, industrial spectral lines, or controlled rhythms alien to nature's chaos. Yet none fit perfectly, each answers some riddles while spawning others. Natural models demand unlikely compositions. Exotic ones lean on untested physics. The artificial one dares us to imagine alien craft. The Comet label is crumbling. When an object defies every expectation, you don't double down, you redefine. 3 Atlas may be forcing us to rewrite what we think we know about the cosmos. Part 5. Defining the challenge with precision. What would it take to undeniably prove something is not natural? Let's set a clear, unshakable standard, a line in the sand. We need to pinpoint exactly what evidence would shatter the natural explanation and compel us to seriously consider an artificial origin. This isn't about guesswork. It's about establishing rigorous, testable criteria that would convince even the most skeptical scientists. First criterion: a structure, defying known physics. Imagine capturing an image of Atlas with such clarity that its form is unmistakable. If that form revealed sharp edges, perfect right angles, symmetrical patterns, or moving components, it would demand attention. Natural objects shaped by accretion collisions and gravitational forces are rough, irregular, and lack geometric precision. A sphere, unremarkable as spheres, naturally minimize surface energy. But a cube, a cylinder, or articulated parts moving in concert that would beg for an explanation beyond nature's playbook. Second criterion: spectral signatures that don't belong. Comets reveal water, carbon dioxide, carbon monoxide, and organic molecules, compounds we expect from primordial origins. But what if spectroscopy uncovered technetium, a product of nuclear reactions or industrial compounds, like synthetic polymers or isotope ratios unseen in nature? That would raise a glaring red flag. The universe crafts a limited palette of chemicals through stellar nucleosynthesis and natural chemistry. Anything outside that palette demands scrutiny. Third criterion, multiband imaging anomalies. Picture taking images of Atlas across different wavelengths and overlaying them. Natural objects follow predictable patterns. Hot regions emit more infrared dust scatters. Optical light and gas emits at specific wavelengths. If the images don't align as physics dictates, if one band shows structures absent in others, that hints at something far more complex than standard thermal or scattering processes. Fourth criterion, metadata and telemetry integrity. Data provenance is critical. Spacecraft observations come with raw frames containing headers, timestamps, instrument settings, checksums, and calibration data. These can be verified against mission logs. Inconsistencies might suggest tampering, but robust, verifiable metadata strengthens any extraordinary claim. You can't prove something groundbreaking with data you can't trust. Fifth criterion, correlated signals. Across physical domains. Imagine Atlas displaying synchronized optical flares, radio bursts, X-ray flashes, and neutrino detections, all perfectly timed. Natural phenomena like blazars, pulsars, or supernovae produce multi-wavelength emissions, but their patterns are familiar. A novel, unexplained correlation across these domains would challenge our understanding and demand a fresh explanation. History underscores the stakes. The Apollo program's data tapes were nearly lost, some recorded over others degraded, requiring restoration decades later. Astronomical archives face similar woes, mislabeled data, deteriorating media, or lost institutional knowledge when key experts retire. The quality of evidence is as vital as the evidence itself. Then there's the human element. Mission teams face immense pressure. Careers hinge on successful missions, publishable results, and defensible claims. National interests can lead to classified or embargoed data unrelated to scientific merit. The fear of ridicule looms large, shaping what gets said and what stays silent. The bar is high, but it must be. Extraordinary claims require extraordinary evidence, and only by meeting these criteria can we move from speculation to certainty. No scientist wants to be the one who cries aliens only to be proven wrong. The professional fallout would be devastating. So what does a credible data set look like? It starts with raw, uncompressed frames, unprocessed, unenhanced, and untampered. These frames must include complete metadata headers verifiable against independent mission logs with checksums to confirm the data's integrity. Multiple observations from different instruments cross-corroborating each other are essential. Open access is non-negotiable, allowing independent analysts to scrutinize the data and replicate findings. Ideally, a documented chain of custody tracks the data from capture to storage to release. Any video claim or announcement about Atlas must meet these unforgiving standards. If someone claims spacecraft images reveal something extraordinary, the first questions are: where are the raw frames? Can we verify the metadata? Is the data openly accessible? Without this level of transparency, we're left with ambiguous observations that spark more questions than answers. The burden of proof for extraordinary claims is and should be immense. Science advances through rigorous evidence demanding reproducibility and rejecting claims fueled by excitement alone. Yet science also thrives by chasing anomalies, by taking seriously the observations that don't fit. The Atlas data is intriguing enough to demand attention, but not yet conclusive enough for firm answers. What comes next hinges on access to decisive observations, whether new data clarifies or complicates our understanding, and whether the scientific community can balance skepticism with open-minded curiosity. The framework is set. The criteria are clear. Now we wait to see if the evidence rises to the challenge. Part 6, ASCAP J1932, a cosmic heartbeat that rewrites the rules. Let's take a step back from the interstellar enigma of Atlas and dive into a mystery unfolding right in our own Milky Way, a discovery so strange it's forcing astronomers to rethink the very nature of the cosmos. Deep within our galaxy, an object named ASCAP J32US0911 is pulsing with the eerie regularity of a cosmic heartbeat, emitting synchronized bursts of radio waves and X-rays every 44 minutes. This celestial oddity, detected by the cutting-edge Australian Square Kilometre Array Pathfinder ASCAP and NASA's Chandra X-ray Observatory, is unlike anything we've seen before, challenging our understanding of the universe and hinting at secrets we've yet to unravel. The discovery of ASCAP J1832 emerged from a sweeping survey designed to catch transient radio sources, those elusive cosmic objects that flicker, flare, or vanish over time, defying the steady glow of stars or galaxies. These transients are the universe's way of keeping us on our toes, and ASCAP J1832 is a standout. Classified as a long-period transient LPT, it belongs to a rare and poorly understood group of objects that pulse in radio wavelengths on timescales ranging from tens of minutes to hours. Most LPTs are already cosmic oddballs, refusing to fit neatly into any known category of astronomical phenomena. But ASCAP J1832 takes it to another level. It's the first object ever observed to pulse in both radio waves and X-rays at the same time, a dual-signal symphony that's as mesmerizing as it is perplexing. The data paints a vivid picture. Every 44 minutes, ASCAP J1832 emits a sharp 2-minute burst of radio waves, then falls silent for 42 minutes before bursting again. This cycle repeats with the precision of a cosmic metronome, unwavering and relentless. When astronomers turned Chandra's X-ray gaze toward it, they found something even more astonishing: X-ray pulses that align closely with the radio bursts, not perfectly overlapping, but clearly correlated in a way that suggests a single, extraordinary mechanism at work. Located roughly 15,000 light-years away in our galaxy, ASCAP J1832 doesn't seem to be nestled in any obvious stellar nursery nebula or star cluster, making its isolation as intriguing as its signal. So what could possibly produce such a bizarre clockwork signal? Astronomers are scrambling for answers, but every hypothesis feels like a leap into the unknown. The first suspect is a magnetar, a type of neutron star with magnetic fields so powerful they could disrupt the fabric of reality itself. Magnetars are known for their pulsing emissions driven by their intense magnetic energy. But there's a catch: their pulses typically flash in milliseconds or seconds, not a leisurely 44 minutes. For a magnetar to produce ASCAP J1832's signal, it would need an entirely new configuration, one that somehow stores magnetic energy over long periods and releases it in these slow, rhythmic bursts. No such model exists, and the physics behind it remains a tantalizing mystery. Another possibility is an ultra-compact white dwarf, the dense Earth-sized remnant of a star that's burned out its nuclear fuel but still spins with a magnetic field. If such a white dwarf were rotating with a 44-minute period, an unusually slow pace for these objects, and if it were undergoing synchronized accretion or magnetic reconnection events, it might produce periodic pulses. But this theory too stumbles. Most white dwarfs either spin much faster or have shed their magnetic fields entirely, leaving them incapable of such feats. The 44-minute timing feels like a cosmic anomaly, defying the behavior we expect from these stellar corpses. Could it be a binary system? Imagine two objects, a pair of stars perhaps, or a star and a compact companion locked in a tight orbit with a 44-minute period. Their interactions, like accretion of material or tidal heating, could trigger periodic flares that align with the observed pulses. But here's the problem. A 44-minute orbital period means the objects are so close together that they should either have merged long ago or be spiraling inward, rapidly bleeding energy as gravitational waves. The math doesn't add up easily, and no standard binary model fits without invoking special conditions or fudging the parameters. Each explanation magnetar white dwarf binary system requires stretching our understanding of physics, tweaking variables, or explaining away inconvenient observations. And this is where ASCAP J1932's story intersects with the enigma of Atlas, the interstellar visitor that's captivated us with its optical and infrared anomalies, but lacks confirmed radio or X-ray signals. At first glance, the two seem worlds apart. ASCAP J1932 is a galactic object likely tied to stellar processes pulsing in radio and X-rays. Atlas, by contrast, is a cosmic wanderer from beyond our galaxy, showing quirks in entirely different wavelengths. They appear to be distinct phenomena separated by context and behavior. Yet ASCAP J1832's existence carries a profound lesson. If one object in our own galaxy can shatter every known category, producing a signal that defies explanation, then we must approach other cosmic anomalies like Atlas with humility and open minds. This discovery underscores how much we still don't know. The ASCAP array, a relatively new tool in the astronomer's arsenal, and Chandra peering into the X-ray universe since 1999 remind us that our view of the cosmos is limited by where we point our instruments. ASCAP J1832 could have been pulsing for thousands, perhaps millions of years, unnoticed until now. How many other strange objects are out there hiding in plain sight, waiting for the right telescope or the right moment to reveal themselves? This realization shifts the probabilities. Before ASCAP J1832, a claim of weird multi-wavelength periodic signals might have been dismissed as instrument error or misinterpretation. Now we know such signals are real, even if we can't explain them. That should make us think twice before brushing off Atlas's peculiarities just because they don't fit our existing models. This also points to a broader strategy for discovery. When you stumble upon one anomaly, the smart move is to hunt for others, looking for patterns that might tie the universe's oddities together. Could there be a connection between ASCAP J1832 and Atlas, some shared physics that links a galactic heartbeat to an interstellar traveler? It sounds like a stretch, but dismissing it outright would be a mistake. The universe thrives on surprises, and ASCAP J1832 is a reminder that we're still cataloging its tricks. Maybe the answer lies in exploring more anomalies, chasing the signals that don't make sense, and staying open to the possibility that the cosmos has more in store than we ever imagined. Part 7. Cross-links. Is there any conceivable physics linking ASCAP J1832 and Comet 3I Atlas? Let's set the stage clearly. No concrete evidence ties these two objects together. They exist in entirely different realms. ASCAP J1832, a mysterious astrophysical source pulsing with precision, and Atlas, a humble comet of ice and rock drifting through our solar system. They differ in scale, composition, and context, yet the exercise of exploring potential connections, however speculative, is far from futile. By probing whether exotic physics could bridge these disparate phenomena, we sharpen our understanding of both and uncover new avenues for observation. This isn't about asserting a relationship. It's about asking whether shared mechanisms might manifest in wildly different regimes and what we'd need to test to find out. Start with the energy scales where the contrast is stark. ASCAP J1932 emits powerful radio and X-ray pulses signaling processes of immense energy. Radio emissions might arise from synchrotron radiation, where charged particles spiral through intense magnetic fields, or from coherent plasma processes, where collective particle behavior generates waves. X-rays demand even higher energies, potentially from scorching hot plasma magnetic reconnection events, or particles accelerated to relativistic speeds. These are the hallmarks of extreme astrophysical environments. Think neutron stars, black hole, accretion disks, or other cosmic powerhouses. Compare that to a comet like Atlas, a modest body of ice and dust gently warmed by the sun's rays. Comets are low-energy systems, their activity driven by solar heating that sublimates ice into gas, forming a glowing coma and tail. At first glance, the two seem worlds apart. But let's dig deeper. Could Atlas harbor or generate magnetic fields capable of mimicking, even faintly, the processes seen in ASCAP J1832 comets? Do possess induced magnetospheres. When the solar wind, a stream of charged particles from the sun, collides with a comet's ionized coma, it creates weak, transient magnetic fields. These are nothing like the organized, intense fields of magnetars or accretion-powered systems, but they exist. Suppose Atlas were an outlier carrying an unusually strong internal magnetic field, or entraining charged particles that form dynamic field structures. Could such conditions produce detectable radio emissions? Plasma physics offers tantalizing possibilities. Coherent radio signals can emerge from plasma instabilities, regions of sharp charge density gradients, or boundary layers where different plasma populations interact. As Atlas vents gas, solar ultraviolet radiation ionizes it, creating a plasma-rich coma. This plasma could, in theory, support waves instabilities or emission mechanisms capable of producing radio signals. Normally, such emissions from comets are too faint to detect with current instruments. But under extraordinary conditions, say an extreme charge density in the coma, or a peculiar magnetic configuration, those signals might cross the threshold of observability. Imagine Atlas passing close to the sun, its coma swelling with ionized gas interacting vigorously with the solar wind. Could this amplify plasma-driven emissions to detectable levels? The challenge lies in the timing. ASCAP J1832 pulses with metronomic precision every 44 minutes, a rhythm suggestive of rotation, orbital motion, or resonant oscillation in a compact object. Atlas, by contrast, shows no such rapid periodicity. Its optical variations tied to gas and dust outbursts unfold over days or weeks, not minutes. For a shared mechanism to hold, it would need to operate across an enormous range of timescales, which feels like a stretch, unless a universal physical process scales dramatically differently in these two contexts. Now consider X-rays. Comets are known to emit faint X-rays, a phenomenon observed in objects like Comet Hyakutake and others. This emission arises from charge exchange, where high-energy solar wind ions collide with neutral atoms in the coma, stealing electrons and releasing X-ray photons. It's a real but subtle process, requiring sensitive instruments like the Chandra X-ray Observatory to detect. If Atlas has an unusually dense or active coma, perhaps due to a high gas production rate or intense solar wind interaction, X-ray emission wouldn't be surprising. But would it mimic ASCAP J1832's pulsed X-rays? Charge exchange in comets is typically steady, not periodic, lacking the structured timing seen in ASCAP J1832. For Atlas to produce pulsed X-rays, we'd need an additional mechanism, perhaps a dynamic magnetic field modulating the emission, or a synchronized outburst cycle, which seems unlikely given current observations. Let's venture into a speculative hypothesis to tie these threads together. Imagine a class of objects, natural or otherwise, defined by strong localized magnetic fields and dense plasma environments. In the galactic arena, where stellar mass compact objects dominate, this manifests as ASCAP J1832, a source of regular pulses driven by rotation or oscillation, with radio and X-ray emissions fueled by plasma processes or relativistic particle acceleration. In the quieter interstellar realm, a smaller object like Atlas could exhibit the same physics on a diminished scale. Its magnetic fields might shape an enhanced coma drive unusual gas-to-dust ratios, or produce faint radio bursts too brief or weak to have been detected. Perhaps during perihelion, when solar-wind interactions peak, Atlas could generate transient radio or X-ray signals mimicking in miniature the behavior of its galactic counterpart. This hypothesis isn't just a thought experiment, it yields testable predictions. If Atlas and ASCAP J1932 share underlying physics, we should search for specific signatures. First, look for faint radio pulses from Atlas, especially during its closest approach to the Sun, when solar-wind interactions are strongest. Second, monitor for X-ray flashes correlated with optical brightening or gas production events, which could indicate enhanced charge exchange or plasma activity. Third, examine the polarization of Atlas's scattered light for signs of organized magnetic fields, a hallmark of structured plasma environments. Fourth, check for Faraday rotation in background radio sources viewed through Atlas's coma, which could reveal the strength and geometry of its magnetic field. Finally, hunt for neutrino detections, tied to either object, as high-energy particle acceleration could produce these elusive particles. Most of these observations remain unattempted. Radio telescopes haven't systematically monitored Atlas at high time resolution, and X-ray observatories may not have targeted it during its active phases. The data to confirm or refute this connection may simply not exist yet. Even if this exploration leads to a dead end, the effort is far from wasted. Observing Atlas at radio wavelengths during its next active period and detecting nothing would be telling. It would rule out coherent plasma emission synchrotron radiation or other radio-producing mechanisms, narrowing the range of possible models for cometary behavior. Conversely, detecting radio pulses, X-ray correlations, or any of the predicted signatures would be groundbreaking. It would suggest Atlas is no ordinary comet engaging in processes that echo those of active stellar objects like ASCAP J1932. Such a finding would propel us into uncharted territory where standard explanations crumble and we're forced to consider radical alternatives, perhaps even mechanisms beyond conventional astrophysics. The beauty of this exercise lies in its systematic approach. Anomalies in one object can illuminate anomalies in another. By comparing across phenomena, patterns emerge revealing how nature might repurpose the same physics in wildly different contexts. ASCAP J1932 and Atlas may seem like an unlikely pair, but exploring their potential connections forces us to refine our questions, design better experiments, and remain open to the unexpected. Sometimes the most outlandish ideas uncover truths, because the universe is far more creative than our models allow. We won't know until we look, and the answers, whether they confirm or debunk this hypothesis, will push our understanding of the cosmos forward. Part 8. The 220 PV ghost particle. A single neutrino changed everything. On an otherwise ordinary day deep beneath the Mediterranean Sea, the KM3NT detector array captured something that defies our current understanding of cosmic ray physics. A neutrino carrying an astonishing 220 peta-electron volts, PeV of energy, tore through the detector, leaving a fleeting trail of light that hints at the universe's most violent processes. To grasp the significance, we need to unpack what this means, because numbers at this scale stretch beyond intuition. 1 peta-electron volt is 1,000,000 billion electron volts. For context, the protons accelerated in the Large Hadron Collider, humanity's most powerful particle accelerator, reach energies of about 14 tera electron volts TeV or 14 trillion electron volts. This neutrino was packing 16,000 times more energy than those protons. It's a cosmic projectile fired by a source so powerful that our theories struggle to fully explain it. Neutrinos are often called ghost particles for a reason. They glide through matter as if it doesn't exist. Right now, billions of neutrinos from the sun are streaming through your body, through the Earth, and out into space, rarely interacting with a single atom. With almost no mass and no electric charge, they're nearly invisible to ordinary matter. Detecting a neutrino requires extraordinary measures, vast volumes of transparent material, like ice or water laced with ultra-sensitive sensors. These watch for the rare moment when a neutrino collides with an atom, producing a charged particle that moves faster than light, can travel in that medium, emitting a telltale flash of Cherenkov radiation. KM3NT, nestled in the Mediterranean, uses the sea itself as its detector. Arrays of light sensors suspended on cables monitor cubic kilometers of water for these fleeting bursts of light. In this case, the ARCA component of KM3NT recorded a distinct pattern, a muon track allowing physicists to work backward and calculate that the neutrino carried at least 220 POO of energy. Rigorous analysis has ruled out errors or misidentification. This event is real. Why does a single neutrino matter? Because a particle with this energy points to cosmic accelerators operating at scales we're only beginning to comprehend. The prime suspects are blazars, supermassive black holes at the hearts of galaxies, actively feeding and launching relativistic jets of plasma at near-light speeds. These jets can accelerate protons to staggering energies, and when those protons collide with ambient photons or matter, they produce pions that decay into neutrinos. Another possibility is gamma-ray bursts, the explosive death throes of massive stars, collapsing into black holes, unleashing torrents of energy. Whatever the source, it's operating at the ragged edge of physics, pushing particles to energies that dwarf anything we can replicate on Earth. The implications are profound. Neutrinos like this one act as cosmic messengers carrying clues about processes and environments we can't directly observe. Unlike charged particles, which get deflected by magnetic fields, neutrinos travel in straight lines pointing directly back to their origins. Pinpointing the source of this 220 PeV neutrino could reveal a natural accelerator of unimaginable power, perhaps a blazar, a gamma-ray burst, or something even stranger. But the discovery also raises questions that ripple beyond its immediate context, inviting speculative connections worth exploring. Could this neutrino tie into the mysteries of objects like ASCAP J132 or Comet 3I Atlas from earlier discussions? The link is tenuous but intriguing. If ASCAP J1832 with its precise radio and X-ray pulses is driven by a compact object like a neutron star or black hole, it might also produce high-energy particles capable of generating neutrinos through collisions in its environment. Similarly, if Atlas exhibits anomalous behavior, say unexpected magnetic fields or plasma processes, could it in some extreme scenario contribute to particle acceleration on a smaller scale? The timescales and energy regimes differ vastly, but the underlying physics of particle acceleration and plasma interactions might share common threads. For now, this is a hypothesis, not a conclusion. What makes this neutrino a game-changer is its call to action. It demands we refine our models of cosmic accelerators, deploy more sensitive detectors, and trace the particle's path to its source. KM3NT and its counterparts, like IceCube at the South Pole, are our windows into this realm. Future observations could reveal whether this 220 POV event is a fluke or a glimpse of a broader population of ultra-high energy neutrinos. If we detect more, we might map the universe's most extreme engines, from black holes to collapsing stars. And if those observations intersect with anomalies in objects like ASCAP J1832 or Atlas, we could uncover a deeper unity in the physics governing disparate phenomena. A single ghost particle has opened a door to the extreme, and the universe is daring us to step through. Could Comet 3I Atlas, an interstellar wanderer, be entangled with a high-energy astrophysical environment? This object, hailing from beyond our solar system, carries a rough trajectory. We can trace back into the galaxy, but its journey remains a mystery. What did it encounter in the vast interstellar void? Did it drift through a supernova remnant brush past a pulsar wind nebula, or traverse regions where intense magnetic fields and dense plasmas create particle acceleration zones? The speculation stretches further. If Atlas harbors exotic matter unknown fields or undetected properties, could it interact with the solar wind or interplanetary medium in ways that produce high-energy particles? Could it even seed neutrino production through mechanisms unheard of in typical comets? These interactions might have left imprints, perhaps in the form of embedded charged particles, altered surface composition, or even exotic matter trapped within its structure. Alternatively, Atlas itself might possess intrinsic properties, unusual magnetic fields, anomalous charge densities, or hypothetical exotic materials that make it more than a typical comet. Now consider its arrival in our solar system. The solar wind, a stream of charged particles from the sun, interacts with comets to form induced magnetospheres and ionized comas. For a standard comet, this interaction is weak, producing faint phenomena like low-level X-ray emission from charge exchange. But if Atlas is carrying enhanced magnetic fields or exotic matter, its interaction with the solar wind could be far more dramatic. Could it generate plasma instabilities or particle acceleration zones within its coma? Could these processes produce high-energy particles capable of spawning neutrinos, ghostly particles that, as we saw with the 220 PeV event signal, extreme physics? This idea pushes the boundaries of cometary science, but Atlas's anomalies, its unexpected brightness, unusual gas-to-dust ratios, or potential magnetic signatures, demand we consider unconventional possibilities. A concrete test exists to probe this hypothesis. Neutrino detectors like KM3NET in the Mediterranean ice cube at the South Pole and others maintain continuous time-stamped and directionally resolved monitoring of the sky. These instruments are designed to catch the rare interactions of neutrinos with matter-producing flashes of Cherenkov radiation that reveal their energy and origin. If a burst of high-energy neutrinos were detected, coincident with Atlas's perihelion passage when solar wind interactions peak, or during its active phases marked by optical or spectroscopic anomalies, the correlation would be significant. The probability of a random coincidence can be calculated using statistical methods, accounting for the detector's field of view, the timing of Atlas's activity, and the expected background neutrino flux. A strong correlation would suggest a physical connection, implying that Atlas is either producing neutrinos itself or interacting with an environment that does. This approach isn't new. It's the cornerstone of multi-messenger astronomy, which correlates signals across different cosmic messengers, light neutrinos, cosmic rays, and gravitational waves. Each messenger reveals unique aspects of a source, because each arises from distinct physical processes and travels through space differently. Neutrinos are particularly valuable because they're nearly unstoppable, passing through gas dust and entire planets without deflection. Atlas, with its interstellar origin and anomalous behavior, could be another entry in this growing inventory of cosmic weirdness. Perhaps it's just a comet with an unusual composition, and we're overcomplicating things. But what if it's something more, a relic of an extreme environment, a carrier of exotic physics, or a trigger for particle acceleration in our solar system? To find out, we need to leverage existing data and plan new observations. Neutrino archives from KM3NeT ice cube and other detectors may already hold clues waiting to be correlated with Atlas's trajectory perihelion timing or active phases. Radio telescopes could search for faint transient signals from Atlas, especially during periods of high activity. X-ray observatories could monitor for charge exchange emissions or unexpected bursts. Atlas's anomalies, combined with the growing evidence of cosmic extremes, urge us to keep observing, correlating, and questioning. Part 9. Space Weather Overlay. While our gaze has been fixed on distant enigmas, pulsing astrophysical oddities, interstellar wanderers, and ghostly high-energy particles, a far more immediate force has been stirring up chaos right in our cosmic backyard. The Sun, that unassuming star at the center of our solar system, has erupted into a frenzy of activity, unleashing 4 coronal mass ejections (CMEs) in rapid succession. These billion-ton behemoths of magnetized plasma hurled from the Sun's corona are barreling through space at speeds topping millions of kilometers per hour, with Earth squarely in their crosshairs. Expected to slam into our planet's magnetic field from October 15 through 17, 2025, they promise a double-edged spectacle, breathtaking auroras for skywatchers and a gauntlet of headaches for astronomers peering at faint targets like Comet 3I Atlas. For aurora enthusiasts, this is a golden hour. Geomagnetic storms triggered when these CMEs tangle with Earth's protective magnetic bubble funnel, charged particles into the upper atmosphere near the poles. There they collide with gases like oxygen and nitrogen, igniting the ethereal dance of lights we know as the northern or southern lights. The more intense the storm, the farther equatorward the auroras stretch, potentially draping their vibrant curtains across mid-latitudes from northern U.S. states to southern Canada and beyond. Forecasts from NOAA and the UK Met Office paint a vivid picture: G1 to G2 minor to moderate geomagnetic storms, fueled by the clustered arrivals from sunspot region AR4246's M-class flares between October 11th and 13. Clear skies could transform ordinary nights into symphonies of green, purple, and red, a rare treat amid the sun's ramp-up towards solar maximum. But for astronomers hunting elusive signals from objects like Atlas, this solar tantrum is a curse wrapped in beauty. The very particles painting the skies also sow discord in our instruments. Radio telescopes vital for probing potential emissions from Atlas fall victim to ionospheric scintillation, fluctuations in the ionized upper atmosphere, warp incoming signals, causing them to flicker and fade like a bad connection in a storm far more disruptive than the gentle twinkle of stars. Cosmic ray showers amplified during geomagnetic unrest pummel detectors with spurious hits mimicking faint astrophysical whispers and muddying the data. Optical scopes aren't spared either. Airglow, the subtle luminescence from excited atmospheric molecules, swells the background noise, washing out the delicate glow of a distant comet's coma. Up in orbit, the assault intensifies. Spacecraft instruments endure direct barrages from solar energetic particles, which can flip bits in electronics, garble telemetry, or spawn phantom detections. Star trackers, those unsung heroes maintaining a satellite's orientation, get bamboozled by high-energy particles, registering as bogus stars, sending craft into disorienting spins. Camera sensors erupt in noise spikes, hot pixels and streaking trails from cosmic ray punctures, turning pristine images into glitch-riddled mosaics. Post-processing filters can scrub much of this away, but perfection is elusive. Subtle artifacts linger, whispering doubts into every analysis. This is where space weather's shadow grows long and treacherous, offering a veil of plausible deniability for data woes. Missing frames in an archive blame a CME's timing. Images riddled with unexplained artifacts point to solar energetic particles. Telemetry blackouts invoke a forced safe mode amid the storm. These aren't fabricated excuses, They're bona fide hazards etched into the annals of space operations. Yet their very legitimacy makes them shields for deeper issues. How do you pierce the fog to discern true environmental sabotage from overlooked errors, rushed protocols, or even withheld revelations? Scrutinize the signatures, cosmic ray strikes etch razor-sharp spikes in isolated pixels or tiny clusters. Ionospheric twinkles follow predictable rhythms and frequency quirks. Safe mode logs spit out unmistakable telemetry fingerprints. With full metadata at hand, the raw diagnostics calibration frames pre- and post-event baselines, you can usually unravel the truth. The rub comes when access is throttled. If you're handed a curt note, "Data lost to space weather," sans the granular logs instrument readouts or contextual frames, verification evaporates. It might be gospel, it might gloss over a tangled web of failures, or it could mask something altogether unrelated, from hardware quirks to human oversight. This isn't the stuff of conspiracy, it's the bedrock of scientific rigor. Claims demand verifiable chains of evidence, and evidence hinges on provenance, the unblemished trail, from telescope lens to final dataset. When that chain frays snapped by vague summaries or archival gaps, the data's trustworthiness erodes, undermining conclusions from the prosaic to the paradigm-shifting. History echoes with cautionary tales. The Hubble Space Telescope's NICMOS instrument suffered a chilling demise in 1999, initially pinned on vague thermal woes, only for deeper dives to unmask a cascade of mechanical gremlins that languished undiagnosed for years. NASA's Mars Observer vanished in 1993 during orbital insertion, its final telemetry hinting at a ruptured fuel line. But the data's incompleteness fueled a thicket of alternative narratives, from sabotage to sensor glitches. In both cases, ambiguity bred delay, eroding trust, until exhaustive probes restored clarity. For Atlas, pieced together from a motley fleet of instruments, this vulnerability looms large. Ground-based scopes battle atmospheric whims and cloud cover. Space telescopes grapple with radiation fluxes and thermal swings. Radio arrays wrestle ionospheric ghosts. Divergent results across this ensemble beg the question: are discrepancies born of Atlas's true peculiarities, or the fingerprints of disparate environmental gauntlets? These 4 inbound CMEs cresting this very week drape yet another shroud of uncertainty over the proceedings. Observations snatched in this turbulent window must wrestle amplified backgrounds, erratic instrument quirks, ballooning error margins, and meticulous recalibrations. The yield isn't junk, far from it, but the widened error bars inject ambiguity, blurring the line between Atlas's quirks and observational illusions. And here's the nagging temporal riddle. If game-changing spacecraft snapshots of Atlas lurk in the vault's frames, poised to dispel the enigmas we've dissected, why the radio silence amid this solar sideshow space weather hands a silver-plated alibi for any stall? The CMEs snarled our pipelines. Bear with us. An announcement now would dovetail seamlessly, quelling speculation without a ripple. Its absence telling, if not damning, perhaps mere bureaucratic inertia, or a prelude to something withheld. Space weather embodies the structural haze veiling our cosmic pursuits. It muddies the path from object to observer instrument, to archive raw capture to polished insight. Some opacity stems from inexorable physics particles, pierce shields, plasmas, warp waves. Some from text tethers, sensors saturate, processors falter. And some, inescapably, from the human weave institutional rhythms, procedural mazes, priorities that clash with transparency's demands. To dispel this fog, we crave redundancy. A chorus of instruments from Hubble's gaze to ALMA's ears, cross-verifying each whisper. We hunger for diverse tactics, amateur feeds alongside pro arrays, archival deep dives paired with real-time streams. We thirst for candor timestamps on every exposure, quality flags waving like beacons, pipelines laid bare for scrutiny. Above all, we need an ethos where provenance queries aren't barbs, but badges of inquiry woven into science's fabric. In Atlas's shadow, as CMEs cascade and auroras blaze, this imperative sharpens. The universe doesn't yield its secrets easily, but neither should our tools obscure them. By fortifying the data's spine against solar fury and human frailty, we edge closer to truths that shimmer brighter than any polar light. Part 10: Instruments, Biases, and the Archive. The hidden flaws in our cosmic view. Let's dive into the journey of an observation from the instant a photon strikes a detector to the moment its data becomes accessible. This intricate, often overlooked pipeline shapes our understanding of the cosmos. Yet it's riddled with pitfalls where information can vanish, distort, or remain locked away. It all begins at the detector. A photon hits, delivering its energy and generating a signal. That signal transforms into a digital value, a number capturing brightness at a precise pixel and moment. But even here, information slips away. The conversion process introduces noise, quantization errors, and variations in detector sensitivity. Cosmic rays and charged particles relentlessly bombard the sensor, producing false signals that must be filtered out. Hot pixels, dead pixels, and column defects create patterns in the data that have nothing to do with the stars. Then comes compression. Raw detector frames are massive, often hundreds of megabytes, for a single high-resolution image. A spacecraft might churn out thousands of frames in one observation run. There's simply not enough bandwidth to beam all that data back to Earth uncompressed. So it's squeezed down, sometimes using lossless compression to preserve every detail, other times lossy compression, sacrificing less critical data. These choices ripple forward, shaping what science can uncover later. Then there's the ring buffer dilemma. Spacecraft memory is finite. Data is stored, temporarily held, until it can be transmitted, then often overwritten by new observations. If something remarkable happens but isn't flagged as urgent, or if the transmission window closes too soon, those frames could be lost forever, erased, irretrievable. Downlink scheduling is another bottleneck. Deep space network time is a scarce resource, with every mission vying for a slot. When a spacecraft gets its chance to transmit, it sends what mission control deems most critical engineering telemetry to ensure the craft's health, then primary science data followed by secondary observations, calibration frames, or bonus captures, all prioritized by the mission team. If your target of interest is low on the list, its data might languish for weeks or months. Once data reaches Earth, it enters the archive pipeline, facing another gauntlet of processing. Raw frames are converted to standard formats, with metadata, target coordinates, observation time, exposure, duration, filter settings, quality flags attached. This metadata is the key to finding data later. A single mislabel can render data effectively lost, even if it sits in storage. Archives evolve, migrating to new systems and reindexing as software advances. Each transition risks errors, file corruption, checksum mismatches, or broken links between data and metadata. In massive archives, housing millions or billions of files, some fraction is almost certain to be damaged, mislabeled, or inaccessible due to glitches. Then there's the issue of access. Embargo periods and proprietary data rights often grant mission teams exclusive use of their data for months or years before it's released publicly. This safeguards the scientists who designed the instruments and observations, giving them time to analyze and publish before others can claim their discoveries. This restricted access, while understandable, means that potentially groundbreaking data could be locked away in exclusive archives accessible only to a select few and shielded from broader scrutiny. Bureaucratic bottlenecks exacerbate the problem. Releasing data demands resources. Staff must prepare files, draft documentation, verify quality, and configure access systems. Space agencies and observatories, often stretched thin, struggle to keep up. Data release timelines slip, and low-priority observations can languish in internal archives simply because no one has the time to process and share them. History offers striking examples of what's at stake. Reanalysis of Hubble's archival images has uncovered objects missed in initial processing. Decades-old Voyager tapes, presumed lost, were rediscovered in storage, preserving invaluable observations. Amateur astronomers sifting through public archives have spotted comets and asteroids overlooked by professionals. The archive is vast, too vast for any single team to comb through every frame systematically. This creates a structural blindness that permeates all of astronomy, not just Atlas. We're only seeing a sliver of the universe, the part that gets observed successfully, downlinked, properly archived, correctly labeled, and analyzed by someone with the resources and interest to do so. The true cosmos is filtered through this fragile pipeline, leaving us unaware of what we're missing. For Atlas, this has critical implications. First, discrepancies between instruments might stem from pipeline quirks. Tests data processing optimized for stellar photometry may overlook extended comas. Ground telescopes, assuming point sources, could miss faint tails. JWSTC's spectrographs excel at detecting molecular emissions, but lack the wide-field imaging needed to reveal dust structures. Second, the absence of psyche. Images in public archives might result from any number of pipeline failures or delays, none requiring conspiracy or cover-up. Yet explaining the absence doesn't ease the frustration. If observations exist, they should be accessible for analysis. If they don't, we deserve to know why observation windows were missed. Transparency in the process is as vital as the data itself. This points to a powerful research strategy for unraveling Atlas or similar mysteries. Don't rely solely on published papers or official releases. Dive into the archives directly. Download raw frames if available, and reprocess them with fresh assumptions. Hunt for metadata inconsistencies that might reveal mislabeled observations. Cross-check observation logs against archived data to uncover gaps. File access requests or FOIAs to nudge institutions toward openness. Citizen science has a pivotal role here. Amateur astronomers and data scientists, free from institutional pressures or career constraints, can ask bold questions and pursue analyses. Professionals might sidestep. They can collaborate across communities, sharing data and methods. Astronomy's history is rich with amateur contributions, and the digital age makes such participation more accessible than ever. This structural blindness is real but not invincible. It demands persistence, technical savvy, and a willingness to navigate bureaucratic mazes. It calls for coalitions of passionate individuals ready to do the unglamorous work of data archaeology. Above all, it requires relentless pressure on institutions to streamline their data pipelines, accelerate release schedules, and embrace transparency. The data exists. Photons struck detectors, signals were recorded, bits are stored somewhere. The challenge is whether we can access, verify, and analyze them openly. Lemon serves as a real-time reminder of just how fragile comets truly are. A few vanish entirely, destroyed so completely that tracking them afterward becomes impossible. Watching Lemon during its peak visibility isn't just about appreciating a beautiful celestial sight. It's about witnessing a survivor, an object that has endured billions of years in the deep freeze of the Oort cloud. While 3I Atlas hides behind the sun, Lemon offers a worthy substitute, a different comet we can actually observe and study firsthand. If you've never seen a comet with your own eyes, if your experience has been limited to images on screens or diagrams in textbooks, now is your chance. Data for solar system objects, factoring in gravitational perturbations and observation geometry. Go outside before dawn, find a dark spot, let your eyes adjust for 10 to 15 minutes, and scan the eastern sky in Cancer. That fuzzy patch of light, if you spot it, holds ice formed before Earth existed, organic molecules older than life itself, and silicate dust that predates our planet. You're witnessing a messenger from the dawn of the solar system, and in just 2 weeks, it will fade from view. Its brief moment of visibility and its ultimate fate, whether survival or disintegration, remain unwritten. Part 7. The Swan and the Context. Comets often seem to arrive in clusters, or at least that's how it appears to those tracking these icy visitors. The reality, however, is more prosaic. These specs include pixel-scale spectral response readout noise and exposure parameters. At any given moment, countless comets orbit the Sun at varying distances, most too faint to detect without large telescopes. A handful are bright enough to catch the eye of amateur astronomers, and very rarely one becomes spectacular enough to be visible to the naked eye and capture public imagination. The clusters we perceive are largely the result of observational bias and the statistical nature of comet discoveries. Yet they still create windows where comet watchers, alongside Lemon and the vanishing 3I Atlas, another comet designated C2025R2 Swan, has entered the catalog. Swan is named after the solar wind anisotropies instrument aboard the SOHO spacecraft, which observes the sky in ultraviolet wavelengths sensitive to hydrogen emission. Comets produce enormous hydrogen clouds, neutral hydrogen atoms created when water molecules break. These clouds are invisible to optical telescopes, but glow brightly at specific ultraviolet wavelengths, allowing Swan to detect them from vast distances, sometimes spotting comets months before they become visible to ground-based observers. C2025R2 Swan was discovered through its hydrogen corona, that immense invisible cloud enveloping the visible. Follow-up optical observations confirmed the discovery and enabled precise trajectory calculations. The comet is following an elongated elliptical orbit that will bring it to perihelion in early 2026, well after Lemon's close approach, but soon enough to keep comet observers engaged as they prepare their equipment and observation plans. Responses. Early brightness estimates for Swan suggest it might reach magnitude 6 or 7 at perihelion, making it primarily a binocular target, but likely not visible to the naked eye, except under exceptional conditions. These predictions hinge on assumptions about the nucleus size and activity level, both of which remain uncertain. Some comets discovered by Swan have exceeded expectations, brightening dramatically as they near the Sun. Others have disappointed, remaining faint and diffuse despite hopeful predictions. The only way to know for sure is to watch and wait. One intriguing possibility linked to new comets involves meteor showers. As a comet approaches the Sun, it sheds dust that spreads along its orbital path, creating a stream of particles. Stability suggests distinct follow-up actions to pursue. If Earth's orbit intersects this dust stream, the particles slam into our atmosphere at high speeds, typically between 30 and 70 km/s, and vaporize in brilliant streaks we call meteors or shooting stars. Most meteor showers we enjoy annually, like the Perseids in August or the Geminids in December, happen because Earth passes through well-established dust trails left by comets that have made multiple perihelion passages, depositing dust over centuries or even millennia. providing confidence in the findings. New comets making their first journey through the inner solar system can produce unpredictable meteor activity. The dust along their orbits hasn't been evenly spread out by repeated passes and planetary perturbations. Fresh outbursts may create dense clumps of particles, leading to sudden and unexpected meteor displays. Scrutinize metadata for uncatalogued objects that might have been dismissed as noise or artifacts. Human review of candidate detections can uncover what algorithms overlooked. If Earth happens to pass through one of these dense clumps, meteor rates could spike dramatically, potentially creating a meteor storm, with hundreds or even thousands of visible meteors per hour. Such events are rare and notoriously difficult to predict because they depend on the exact spatial distribution of dust, which we cannot measure directly. Swan's orbit will be calculated with increasing precision in the coming months, allowing astronomers to assess whether any potential intersections with Earth's path through its dust streams might occur. Even the mere possibility, however low, of a meteor shower gets Comet and meteor enthusiasts buzzing with excitement. Witnessing a meteor storm is a bucket list experience, a celestial fireworks display that might grace the skies only once or twice per generation. These meteors appear to radiate from a point in the sky called the radiant, a visual effect created by the converging perspective of parallel particle During a storm, the entire sky seems to rain meteors, streaks of light, shooting in every direction, overwhelming the senses in a way that no photograph can truly capture. But for every comet that brightens and dazzles as hoped, several others fizzle out. The history of comet astronomy is filled with predictions that didn't pan out, objects once expected to become great comets that instead remained faint and unremarkable. Data archaeology. Engage science communicators to craft compelling narratives that drive support. Comet Kohoutek in 1973 was predicted to become one of the brightest comets of the century, but barely reached naked-eye visibility, disappointing millions who had been promised a spectacular show. Comet Ison in 2013 was expected to survive perihelion and brighten dramatically, but instead, the comparison between Swan and Lemon's brightness curves will ultimately yield valuable scientific insights. Observing two comets simultaneously under similar solar conditions offers a rare opportunity to directly compare activity levels and sublimation physics. Differences in brightness at comparable distances from the Sun reveal variations in If one comet is water-dominated and the other driven by carbon monoxide, their activity profiles will diverge in distinctive ways. If one fragments while the other remains intact, we gain crucial clues about the structural differences that govern a comet's fragility. Using Swan and Lemon as foils adds a layer of narrative tension. Many comets fail, so will 3 Atlas share that fate? The October 2025 coronal hole event might have been a singular anomaly, or it could herald a phase of heightened solar activity that imperils any comet venturing through the inner solar system. As the Sun's 11-year activity cycle nears its solar maximum, sunspots and coronal mass ejections become more frequent, while solar wind speeds and magnetic field strengths intensify, amplifying the challenges for passing comets. Comets approaching perihelion during solar maximum endure far harsher conditions than those arriving during solar minimum. The history of comet fragmentation offers sobering lessons. Comet Shoemaker-Levy 9's tidal disruption by Jupiter in 1992, culminating in its spectacular impacts in 1994, showed just how completely a comet can be torn apart. By its 2011 return, Comet 73P had shattered into more than 60 identified fragments, creating a sprawling debris field stretching thousands of kilometers along its orbit. Some fragments remained active, generating small comas, while others lay dormant, their volatiles exhausted or locked beneath inactive crusts. These fragmentation events are crucial. A solitary large comet nucleus presents minimal risk to Earth, as the chance of a few kilometer-wide body striking our planet is incredibly slim. However, when a comet fragments, it spawns dozens or even hundreds of smaller pieces, each capable of entering the atmosphere. Although these fragments are individually smaller and less catastrophic than the original nucleus, their sheer number. Most comet fragments harmlessly blaze out in the atmosphere or bypass Earth altogether. Yet the risk landscape shifts dramatically when facing dispersed debris instead of a lone object. Foreshadowing the 60 comet event destined to be the brightest comet, they mark time in human consciousness, unlike the steady rhythms of planets and stars. One generation recalls Halley's Comet in 1986, a view that disappointed many but left a lasting cultural imprint. The generation before witnessed Comet Hale-Bopp in 1997, dazzling the naked eye for months and shining bright enough to be seen from city centers. Today's generation might remember Lemon Swan or Three-Eye Atlas if any of them endure. Are we currently in a cluster period of unusual comet appearances? Statistical analyses of comet discovery rates over decades reveal fluctuations that could indicate genuine clustering, or they might merely mirror advances in detection technology. The Atlas survey, which discovered 3 of the Atlas comets, was designed specifically to detect near-Earth objects with comets as a fortunate bonus. Alongside it, the Catalina Sky Survey, Mount Lemmon Observatory, and Pan-STARRS in Hawaii all operate automated systems that vigilantly scan the skies for anything in motion. And since comets move, they inevitably get spotted. And stops comparing it to solar distance. Any deviations from expected comet behavior would hint at unusual internal structures or energy sources. But there's a tantalizing hint in the data that the Oort cloud, the distant reservoir of comets, might undergo perturbations that send showers of comets plunging toward the inner solar system. Passing stars, gravitational tugs from giant molecular clouds in the galaxy, and even the solar system's vertical oscillation through the galactic plane as it orbits the Milky Way's center, all these forces could shake comets loose, achieving near diffraction-limited resolution. Space telescopes like JWST or HST, unhindered by Earth's atmosphere, can access blocked wavelengths and push resolution further. If real, these comet showers would unfold over timescales of millions of years, far too vast for direct human observation. Yet hidden within the geological record traces of clustered impacts might reveal these ancient storms of comets that pummeled the inner solar system during the reign of the dinosaurs or even earlier in Earth's history. Multi-wavelength imaging can separate dust from gas emissions, while color maps highlight compositional variations. Difference imaging, subtracting images taken at different times, can spotlight changes. Resolving features down to tens or hundreds of meters requires space telescopes or top-tier ground instruments with ideal conditions. Test 4. Coordinated multi-wavelength monitoring. A synchronized observation campaign across radio, X-ray, and optical wavelengths during Atlas's active phase could uncover telling correlations. Optical brightening paired with radio pulses might suggest electromagnetic activity beyond simple thermal glow. X-ray flashes aligned with spectroscopic gas ejections could point to specific plasma processes. Independent variations across wavelengths fit chaotic natural activity, but synchronized behavior would be extraordinary, hinting at organized energy release. This demands intense coordination, advanced planning, and telescope time allocation for what's essentially a speculative hunt. The campaign needs frequent observations to catch short-term events, minutes to hours, and long-term monitoring to establish baselines, days to weeks. The payoff evidence of coordinated processes that natural chaos rarely produces. Test 5. Neutrino and cosmic ray coincidence monitoring. This test is a long shot requiring luck and access to neutrino detector data from facilities like KM3NET or IceCube. Neutrinos are elusive with low detection rates, mostly tied to atmospheric or distant astrophysical sources. But checking for detections coincident with Atlas's active periods is feasible if access is granted. Cosmic ray networks like the Pierre Auger Observatory can also be monitored for excess events during activity. Random coincidences are calculable, so a statistically significant correlation would be staggering, elevating Atlas to a high-energy phenomenon. Comets don't emit detectable neutrinos or cosmic rays. If Atlas does, it's operating beyond standard cometary physics. Test 6: Rotation and Light Curve Analysis. As Atlas rotates, its brightness varies with surface orientation, offering clues about its shape and spin. Detailed light curve analysis can reveal rotation periods, axis orientations, and even rough shapes. Short periods suggest a small, cohesive body. Long periods might indicate a larger object or tidal locking. Large brightness swings point to elongated or irregular shapes, while small variations suggest sphericity or a pole-on view. Unnaturally smooth light curves lacking the irregularities of natural bodies would be suspicious. If gas emissions or brightness changes align with rotation, in ways suggesting control, like localized vents firing at specific phases, that's a major clue. Sustained monitoring over hours to days using automated telescopes and global networks for 24-hour coverage is essential. Standard period finding and light curve inversion techniques can handle the analysis. Test 7: Magnetic field detection via Faraday rotation. Radio waves passing through magnetized plasma twist their polarization angle, a phenomenon called Faraday rotation, proportional to field strength and plasma density. If Atlas has a magnetic field and an ionized coma background, radio sources seen through it should show this effect. This requires Atlas to pass near a bright radio source, a rare but predictable event using orbital and source catalogs. Precise polarization measurements accurate to fractions of a degree are challenging but doable with VLA or other radio networks provided Earth's ionospheric effects are calibrated out. Comets lack intrinsic magnetic fields due to their small, non-metallic nuclei. Detecting one would suggest metallic composition, internal dynamos, or unnatural electromagnetic systems. Each test offers clear predictions. A natural comet should show comet-like polarization activity tied to solar heating, irregular shapes, chaotic light curves, and no magnetic fields. A fragment swarm might show slightly odd polarization, compact, but extended structures and chaotic light curves. An electromagnetically active object could display anomalous polarization, magnetic fields, multi-wavelength correlations, or activity far from the Sun. An artificial object might reveal geometric shapes, organized emissions, or controlled patterns. These tests are falsifiable. Specific results can rule out hypotheses. That's the heart of science: make predictions, test them, and refine beliefs based on evidence. Ambiguous observations that bend to preconceived notions won't cut it. We need decisive data to eliminate possibilities, requiring coordinated effort, telescope time, and a willingness to chase a potentially groundbreaking discovery. The stakes are high. Confirming Atlas as an unusual comet could redefine cometary physics. Finding something entirely different could launch a new field of study. With future perihelion passages and active phases ahead, the question isn't whether opportunities exist. It's whether the astronomical community will seize them or let Atlas remain an enigmatic footnote among interstellar visitors. Part 13: The Monumental Implications of an Artificial Atlas. What if Atlas, or any celestial object we observe, were not a product of nature but an artifact of advanced technology? The mere possibility sends shockwaves through our scientific, political, and cultural frameworks, demanding a radical rethinking of how we search for extraterrestrial intelligence, handle unprecedented discoveries, and validate claims that could redefine humanity's place in the cosmos. If we entertain, even as a thought experiment, the idea that Atlas might be artificial, everything shifts: our SETI strategies, our scientific protocols, our global policies. The stakes couldn't be higher, and the questions couldn't be more urgent. Let's confront the implications head-on. Traditional SETI has long hinged on a narrow premise: intercepting deliberate radio signals, beacons broadcast by technological civilizations eager to make contact. These signals, we assume, would use electromagnetic radiation at specific frequencies originating from distant planetary systems orbiting far-off stars. The approach is methodical, rooted in the belief that communication is intentional, detectable, and tied to recognizable patterns. But what if this paradigm is too limited? What if advanced technology doesn't need to shout across the cosmos? What if instead it travels silently, subtly, arriving in our solar system as artifacts small enough, numerous enough to blend among the millions of natural bodies we track? An artificial object might not broadcast at all. It could lie dormant, observing passively, operating on principles so alien they defy our definitions of communication. This possibility turns SETI upside down. Detection would no longer rely on decoding messages, but on spotting anomalies, physical properties, behaviors, or movements inconsistent with natural processes. A rock tumbling through space follows predictable Newtonian paths. An artifact might not. Its composition could reveal materials or structures unknown to geology. Its motion could hint at purposeful navigation. This shifts SETI's tools from radio telescopes to a broader arsenal: optical surveys to catch glints of unnatural surfaces, spectroscopy to analyze chemical signatures, astrometry to track erratic trajectories. The search space expands exponentially, from scanning distant stars to scrutinizing objects in our cosmic backyard. The thresholds for detection transform as well. Traditional SETI demands a towering bar for claiming artificial signals, wary of the professional and societal fallout from false positives. A physical artifact, however, offers a different calculus. We could study it directly, gathering multiple lines of evidence imagery, spectra, motion data that radio signals can't provide. The question becomes, across every observational method, does this object's behavior align better with artificial origins than natural ones? This shift raises immediate policy dilemmas. Who controls the data if an artifact is confirmed? Space agencies like NASA or ESA currently govern their mission outputs, treating data as proprietary until shared through scientific channels. But the discovery of non-human technology would transcend these norms, potentially triggering a jurisdictional free-for-all. National security agencies might assert authority, viewing an artifact as a strategic asset rather than a scientific curiosity. International bodies such as the UN Committee on the Peaceful Uses of Outer Space could claim oversight, arguing for global responsibility. Yet no legal frameworks exist in actionable form to navigate this uncharted territory. The Outer Space Treaty of 1967 governs peaceful uses of space, but offers no clear guidance for handling alien technology. Scientific disclosure protocols are equally unprepared. The International Academy of Astronautics has SETI guidelines for detecting artificial signals, emphasizing international notification, rigorous verification, and caution before public announcement. But these are voluntary, unenforceable, and built for radio signals, not physical objects. Picture a spacecraft capturing unmistakable images of an artificial structure. Who decides when, how, or even if that information reaches the public? The chain of custody for such data becomes critical. Any claim of alien technology will face a firestorm of skepticism, and rightly so. To withstand it, The evidence must be ironclad, raw data frames with cryptographically signed headers to prove authenticity, multiple independent observations, cross-verifying the phenomenon, open archives, allowing global scrutiny, and transparent methodologies documenting every processing step. Anything less invites accusations of error, fraud, or misinterpretation, undermining the discovery's credibility. The scientific community would need to move with unprecedented precision, ensuring every claim is bulletproof. International coordination would be indispensable but daunting. Nations have divergent interests in space. Some prioritize scientific prestige, others military dominance. Transparency varies widely, as does the relationship between space agencies and defense establishments. An artifact detected by one nation's spacecraft might be classified as a strategic secret, not shared scientific data. Balancing the principles of open science against national security concerns would require delicate, high-level negotiations, likely involving heads of state and global institutions. Historical analogies offer little guidance. The 1967 discovery of pulsars sparked brief speculation about artificial signals before neutron stars explained them. The 1977 WOW signal, still unexplained, hasn't been replicated. Neither case demanded the policy upheaval an artifact would provoke. Closer parallels, like the international collaboration behind DNA's structure or the Manhattan Project's nuclear breakthroughs, hint at the scale of coordination needed, but fall short of capturing the existential weight of alien technology. Ethical questions multiply like stars in the night sky. If an artifact exists, who claims ownership, the nation or agency that finds it? Humanity as a collective, the civilization that created it. Do we have the right to study it, manipulate it, or attempt communication? What if it's observing us, silently gathering data? What if disturbing it triggers responses we can't predict, benign, defensive, or catastrophic? Science fiction has wrestled with these scenarios for decades, from Arthur C. Clarke's monoliths to the probing machines of the Matrix. But these are no longer hypotheticals. They're questions we might face in our lifetime. The risk of premature announcement looms large. Claiming alien technology with insufficient evidence could cripple scientific credibility, derail SETI efforts, and invite ridicule that poisons future claims. Conversely, sitting on evidence out of excessive caution could be reckless if the phenomenon is real and time-sensitive. Finding the balance requires judgment that no protocol can fully prescribe, blending scientific rigor with pragmatic urgency. Public reaction adds another layer of complexity. The revelation of non-human technology could ignite a spectrum of responses. Some would celebrate it as humanity's greatest discovery, a gateway to cosmic kinship. Others might panic, fearing invasion or existential threats. Skeptics, even in the face of robust evidence, might dismiss it as a hoax or conspiracy fueled by distrust in institutions. Managing this societal impact while preserving scientific integrity would be a Herculean challenge. Religious, philosophical, and cultural frameworks would be tested as humanity grapples with its place in a universe no longer solely ours. The closest modern parallel might be the global response to pandemics or climate change issues that demand unified action, but often fracture along lines of belief and interest. Our current frameworks, scientific, institutional, cultural, are woefully inadequate for this scenario. That's not a reason to avoid the question, but a call to prepare now. Scientific investigation would follow the same iterative process that has driven discovery for centuries: observe, hypothesize, predict, test, revise. But the stakes and scrutiny would be unparalleled. Every observation would be dissected by critics hunting for flaws. Every claim would need to withstand the fiercest skepticism. This is appropriate. Extraordinary claims demand extraordinary evidence, and the process of gathering it must be beyond reproach. Yet fear of failure shouldn't paralyze us. The questions are answerable, the observations feasible, the data within reach. What's required is courage to pursue anomalies with seriousness, rigor to avoid false conclusions, and transparency to maintain trust. We're already investigating Atlas, its orbit composition and behavior, but in a fragmented ad hoc way. Every telescope pointed at it, every spectral analysis, every attempt to explain its quirks is part of the process. The question is whether we'll continue with scattered efforts that leave ambiguities unresolved, or mount a focused global campaign to deliver definitive answers. If Atlas is artificial, its signature's unusual structure, exotic materials, purposeful behavior will eventually reveal themselves under sustained scrutiny. Technology can't hide forever. If it's natural, proving so conclusively expands our understanding of the universe's diversity, revealing phenomena we never imagined possible. Either outcome advances science. The pursuit itself sharpens our tools from detection methods to data integrity protocols. It forces us to refine how we'd recognize intelligence in unexpected forms, a machine adrift in space, a probe masquerading as an asteroid, a relic from a civilization long gone. These are questions worth asking regardless of Atlas's true nature. Hesitation or disorganization only delays the inevitable. If we want answers, we need to act with purpose, now building the frameworks to handle the extraordinary if it becomes real. The universe is waiting. Part 14, a cosmic tapestry of the strange. Are we stepping into a new era of cosmic oddities? Zoom out to see the grand design. 3 comets, unlike any before, defy our expectations. Take Atlas, for instance, behaving in ways no comet should. Then there's ESCAP J11332 pulsing in radio and X-rays every 44 minutes, a rhythm that fits no known cosmic category. And a 220 peta-electron-volt neutrino hinting at particle acceleration we can't yet unravel. Are these quirks mere outliers, or is the universe revealing a strangeness we've only begun to grasp? Reflect on the past decade's revolution. Sky-scanning telescopes, Zwicky Transient Facility, Pan-STARRS, and the Vera Rubin Observatory sweep vast celestial expanses, catching every flicker or drift. Radio arrays like ASCAP and Meerkat vigilantly monitor, spotting fleeting events older instruments would have missed. Neutrino detectors have scaled up from modest setups to sprawling cubic-kilometer giants. Gravitational wave observatories have cracked open a new cosmic vista. Each leap in technology unveils phenomena we never knew existed. Fast radio bursts undetected until 2007, not for rarity, but because we weren't looking right now, pop up dozens daily, their origins still elusive. Neutron-star mergers, once theoretical, became real in 2017, spotted through gravitational ripples and light simultaneously. The universe keeps startling us, not because it's changed, but because we're finally seeing it clearly. Machine learning turbocharges this quest. Algorithms now sift through millions of images, spectra, and light curves, spotting patterns and oddities in hours that would take humans years. We're finding anomalies faster than we can explain them, building a catalog of mysteries that outpaces our understanding. But here's the catch. More data breeds more noise. With billions of objects under scrutiny, statistical flukes, rare events happen thousands of times. Instrument glitches get mistaken for signals. False positives abound. How do we separate true cosmic breakthroughs from random quirks? Correlation and replication hold the key. If oddities cluster around specific objects, regions, or times, they hint at something real. If they're scattered, fleeting, and unrepeated, they're likely noise. Atlas is strange, but it's one comet. ESCAP J132 is bizarre, but it's one object. that neutrino a single event. Are they linked? Are we missing others, or are we weaving patterns from thin threads chasing ghosts in the data? Beyond these recent discoveries broaden the mystery. Exoplanets boast impossible atmospheres, orbits that defy formation models, and densities demanding exotic makeup. Stars like tabbies dim, erratically sparking wild theories of alien megastructures before dust clouds steal the spotlight. Galaxies flout expectations, some lack dark matter, others overflow with it, challenging our grasp of cosmic assembly. In 2025, AI-driven astrophysics is soaring. Neural networks spot gravitational lenses, decode unusual spectra, and predict stellar evolution with uncanny precision. But AI sees only what it's trained to see. If training data misses novel phenomena or artifacts, algorithms might dismiss the truly bizarre as noise. We're leaning on tools that could blind us to the unexpected. This raises a deeper question. Are we uncovering genuine cosmic strangeness, or conjuring it through bias? The universe has always been wild quantum mechanics. General relativity, dark matter, and dark energy are all gloriously weird. Each generation of physicists finds reality odder than the last, until the bizarre becomes familiar, yet never stops feeling alien. Perhaps we're in a strangeness era where 21st century tools finally reveal the universe's true wild nature. Extreme conditions, exotic processes, scales and energies that stretch physics to its limits. Atlas, ESCAP, J1832, and ultra-high-energy neutrinos might be early whispers of a vast catalog of cosmic weirdness. Or maybe we're overreaching, seeing patterns in randomness, letting imagination outrun evidence. The only path forward is to keep watching, testing, and taming wild hypotheses with rigorous measurement. Science thrives by chasing what might be wrong, probing deeply enough to know. We're in a golden age of astronomy. Discoveries cascade faster than ever. Questions deepen, answers astonish. Whether Atlas is truly anomalous or merely unusual, our ability to study an interstellar visitor, debate its meaning, and design tests to probe its nature is a leap that would have seemed like science fiction a generation ago. More interstellar objects are coming. Borisov preceded Atlas. Models suggest dozens zip through our solar system yearly, most too faint to spot. When the Vera Rubin Observatory hits full stride, it'll find them by the hundreds. Each is a courier from distant stars carrying clues about alien environments we can't visit. Each tests our assumptions, daring us to admit we might be wrong. The strangeness may just be beginning, and that's thrilling. It's unsettling too, because it means the universe still holds secrets, still springs surprises, still challenges our certainties, and forces us to rethink what's possible. Part 15. Final Synthesis. Let's bring this cosmic enigma back to Earth, distill the known from the unknown, separate hard evidence from tantalizing speculation, and forge a clear, actionable path to answers. The mystery of Three-Eye Atlas demands clarity. Here's what we know, what we must demand, and the three definitive tests that will unlock the truth. What we know. The data is unambiguous in places. Over 9,000 stacked frames of Three-Eye Atlas reveal no extended coma, only a point source, a stark, consistent signal that resists easy explanation. This is no fluke. It's solid, reproducible evidence from rigorous observation. Infrared instruments, including the James Webb Space Telescope JWST, have detected gas emissions, carbon dioxide, and water vapor, pointing to volatile activity within the object. These findings are rock-solid, anchored in precise measurements. Yet ground-based optical telescopes paint a murkier picture. Some report asymmetries in Atlas's structure, hinting at something unusual. Others see little to no discernible structure, suggesting a more conventional object. These observations are real, but frustratingly inconsistent, like pieces of a puzzle that don't quite fit. Meanwhile, spacecraft data, particularly from the Psyche mission, which could hold the key to resolving these contradictions, remains unreleased, leaving us in the dark about whether such data even exists. The gray zone. The ambiguity deepens when we probe the unknowns. What physical mechanism produces gas emissions without a visible dust tail? Is the nucleus of Atlas a shadowy core we can't yet fully characterize, made of familiar comet-like materials or something stranger? Do the conflicting observations stem from genuine anomalies in Atlas's behavior? Or are they artifacts of observational biases, instrument limitations, or data processing quirks? Could electromagnetic or plasma processes be driving unusual activity? And what about the multi-wavelength phenomena we've encountered, ASCAP, J1232, or high-energy neutrinos? Is there any link to Atlas, or are we chasing shadows? The realm of speculation. Then there's the territory of pure conjecture where imagination outpaces evidence. Could Atlas be artificial, a technological construct from beyond our solar system? Is critical data from Psyche or other missions being withheld for reasons unrelated to science, perhaps bureaucratic, political, or otherwise? Might there be a deeper pattern tying Atlas to other cosmic anomalies through exotic, undiscovered physics? These ideas ignite curiosity and demand exploration, but they rest on no firm footing yet. They are hypotheses, provocative and worth testing, but far from facts. The verdict ladder. To move from speculation to certainty, we need a framework, a ladder of explanation. At the base lies the natural explanation. Atlas is a comet or similar object explicable through some combination of composition, structure, and environmental conditions, all within the bounds of known physics. No new rules required, just a clever arrangement of what we already understand. Climb a rung to exotic natural, and we're looking for processes that set Atlas apart from typical comets, perhaps electromagnetic interactions, unusual ice chemistry, or other phenomena still grounded in established physics, but rare or extreme in their expression. At the top, the artificial hypothesis demands extraordinary evidence. Multiple independent lines of proof showing behavior that defies any natural process, structures that suggest intentional design, and data so clean, it rules out error, contamination, or misinterpretation. Each step up the ladder requires more robust, more compelling evidence to justify the leap. 3 tests to settle the mystery. To climb this ladder and uncover Atlas's true nature, we need 3 critical tests, each designed to cut through ambiguity and deliver clarity. Test 1: archival forensic recovery. The most direct path to answers lies in existing data. We must secure access to Psyche spacecraft observations or any other mission data captured during Atlas's active windows. Do these images exist? If so, they could reveal the object's true form, whether it's a typical, irregular nucleus, a cluster of fragments, or something unnervingly geometric. We need to analyze these images for structure and morphology, verify their metadata, and scrutinize their processing history to ensure integrity. This test is technically straightforward, but may face institutional resistance. Formal requests, including Freedom of Information Act (FOIA) filings, will be essential. Persistence can overcome bureaucratic hurdles, and the payoff could be transformative, high-resolution images that show Atlas as it truly is, not as we imagine it to be. Test 2: coordinated multi-wavelength campaign. To capture the full scope of Atlas's behavior, we need a global multi-instrument assault during its next active period. Organize a campaign that combines polarimetry, optical, and infrared spectroscopy to monitor gas production, radio telescopes, to search for emissions, X-ray observatories, to detect flashes, and particle detectors, to watch for high-energy events. This comprehensive approach will reveal correlations that single instruments miss, answering critical questions. Does Atlas exhibit electromagnetic activity? Is its behavior periodic or chaotic? Does it produce signatures no comet should? This test requires coordination across observatories and disciplines, but it's within our reach. It's the scientific equivalent of shining a spotlight on Atlas from every angle, ensuring no detail escapes scrutiny. Test 3. High-energy event correlation. The boldest test probes the most extreme hypothesis that Atlas is tied to high-energy astrophysical processes. Continuously monitor neutrino detectors, cosmic ray networks, and gamma-ray observatories for statistically significant correlations with Atlas's activity. This is a long shot, but the infrastructure exists. Real-time data streams from these instruments can be analyzed rigorously. A positive correlation would upend our understanding, suggesting Atlas is no mere comet, but a player in high-energy cosmic phenomena. A negative result, while less dramatic, would rule out a swath of exotic possibilities, tightening the focus on more conventional explanations. Either way, this test pushes the boundaries of what we believe is possible. The 90-day roadmap. To execute these tests, we need a plan, a 90-day sprint to galvanize action and accelerate discovery. Days 1 to 30. Mobilize the Citizen Audit Coalition. Assemble a diverse team of volunteers, data scientists, astronomers, legal experts, and advocates. Divide tasks for an exhaustive archival search, filing FOIA requests for psyche data and mission logs. Begin systematically downloading and reprocessing images from any mission that might have glimpsed Atlas, ensuring no stone is left unturned. Days 30-60. Build momentum. Compile results from the archival search, identifying gaps and promising leads. Draft telescope proposals for a coordinated observation campaign during Atlas's next active phase. Reach out to neutrino detector collaborations, requesting their expertise in correlation analysis. Launch a public advocacy campaign to demand transparency, rallying support from the broader community to pressure institutions for data access. Days 60-90. Execute and amplify, submit telescope proposals to observatories worldwide. Follow up on FOIA responses, ensuring no request is ignored. Publish preliminary findings from the archival search to spark interest and invite scrutiny. Establish direct communication with professional astronomers willing to contribute expertise or telescope time, building a network of allies in the quest for truth. Engagement, a call to action. This is a mystery we can solve together. If you're a data scientist, dive into archives or develop tools to streamline analysis. If you have access to telescopes, even small amateur ones, join coordinated observation campaigns. If you're a legal expert, guide FOIA requests and navigate data access barriers. If you have a platform or audience, amplify the call for transparency, raising awareness and holding institutions accountable. If you can fund, support citizen science through grants or crowdfunding. Every contribution, no matter how small, accelerates our journey from question to answer. The emotional core. We stand at a pivotal moment. Atlas is strange enough to demand explanation, and our tools, telescopes, spacecraft, data streams are powerful enough to provide it. The easy path is to shrug, call it a peculiar comet, and move on. The courageous path is to admit we don't yet understand and commit to finding out why. Science lives for these moments, when observations defy expectations, when the standard model groans under the weight of anomalies. Do we patch it with quick fixes or dare to question the foundations? Most often the patches hold, and our models grow stronger. But every so often the anomalies point to something deeper, a truth that forces us to rewrite what we thought we knew. Is Atlas a comet with quirks? We can explain a natural but exotic phenomenon pushing the edges of physics. Or in the scenario that feels like science fiction, but cannot be dismissed without evidence the first detected artifact from beyond our solar system. The probability of that last possibility is low, but not zero, and its implications are too profound to ignore, simply because they challenge our comfort zone. The stakes. The mystery of Atlas is wide open. The tools are at our fingertips. The tests are defined. We don't yet have proof of the impossible, but we have the strongest clues we've ever held about something that doesn't fit our cosmic map. The data is out there locked in archives, waiting in the sky, or streaming from instruments right now. The question is whether we have the collective resolve to pursue it, the rigor to do it justice, and the courage to embrace whatever truth emerges. Discovery isn't a sudden epiphany. It's the slow, relentless piling up of anomalies, the dogged pursuit of questions, and the collaboration of curious minds, turning observations into understanding. Atlas invites us into that process, offering a rare chance to distinguish reality from misinterpretation. So let's seize it. Demand the data. Conduct the observations. Run the analysis. Listen to what the universe is telling us. The only thing worse than discovering we're wrong about something fundamental would be having the chance to find out and choosing to look away. The frontier is open. The mystery calls. Somewhere in the data we haven't yet seen, or the observations we haven't yet made, the answer awaits. Let's go find it.